So we're continuing today with our discussion from Chapter 3. And in particular, we'll be talking today about signal space analysis. Very important topic that will expand our ideas from the binary case to the M-ary or larger dimensional space. So we're going to talk about signal space and how this is going to help structure our mathematics in order to do an expansion from binary to more complex modulation. So this is covered in section 3.1 of the Scholar textbook, the part about signal space, the concepts of signal space, but the mechanics of how we find a signal space is called the Schmidt process. I'll be presenting that today. It's not in the book, however, there's lots of information available on the internet about this, and I'm sure if you Google it, you will find more material for reading if you need more explanations. So what have we done so far today? Let's think back about what we've covered. We've looked at how to work with the receiver, and we've looked at the linear sampling receiver, and we have seen that this receiver is a filter followed by a sampler, followed by a decision block. So here, this part refers to the decision block. So we have two strategies. Our decision could be based on maximizing the a posteriori probability, or it could be focused on maximizing the likelihood. And remember, the difference between the two is in that when we have information about the a priori probability of our symbols, then we'll use the map rule. And if we don't have that information, we'll end up using the maximum likelihood rule. Now we also looked at, we said that the receiver had a filter, and the filter that we're looking at, so this is the linear part of the receiver, or the filtering. And we saw that if we know that we're dealing with additive white Gaussian noise, and we want to do the best we can in terms of having a filter that enhances the signal and diminishes the noise, the best we can do is use something that is a filter matched to the waveform of the symbol that's transmitted. We also concluded that the actual symbol itself, that waveform, we never specified. The bound on the signal to noise ratio was based on the energy in that signal. But once I fix the energy of the signal, it really doesn't matter how I shape that waveform. Square wave, triangle, sawtooth, any of the waveforms that I want to use doesn't really change the performance of the receiver. So the big difference so far is that when we come in with specific examples, we've looked at the binary case. We looked at the binary case. What would the decision rule look like for a map, for a maximum likelihood? What does the decision rule look for two symbols? What does the matched filter look for when we have two symbols? However, if we're going to push to modern communication systems, binary signaling is not enough. We really have to expand to a higher dimensional modulation format. And the higher dimensional formats are generally based on M symbols, an arbitrary size to the constellation. So we need to be able to generalize what does our form of our receiver look like, what should our strategies be for the design of our receivers. But we also, not just what I'll say here, receiver design, which is what we've looked at so far. Of course, we started with the linear sampling receiver as sort of being given to us, and then we specified what it exactly would look like. But the next step is also going to be in the bit error rate, and this is the performance of these receivers. And the performance of the receivers generally is characterized by bit error rate, BER, and we want to be, I sort of alluded to that previously because we looked at the PDF, the conditional PDF, and we said the tail of this conditional PDF below the threshold for the decision represented the bit error rate. And that was as much as I said to date, and now we're going to be getting into it a little more in depth because calculating it for two-dimension or larger dimension ends up not being too different, and so I sort of saved it for later. So now we'll be getting to that, but certainly the introduction of signal space is going to be very important for these two, receiver design, receiver performance. So the motivation for moving to this signal space is having the mathematics to attack how I make this decision rule of maximum likelihood, maximum a posteriori, when I'm looking at a situation that is not binary. So in binary, I had an inequality that was very easy. You know, it's like two numbers, one is bigger than the other. Now, when I get to larger constellations, what I need is a little bit more intuition to understand what is going to be the best strategy for my receiver. And this space approach gives us a great deal of geometric intuition. We're already familiar with signal spaces, vector spaces, which are physical spaces, and we have intuition about what it means to manipulate these spaces. And so that intuition is going to help us understand fundamentally differences between different options for different modulations. And it's also going to help us quantitatively when it's time to do the error probability calculation. So this motivation is very strong. Signal space is going to be a big help to us. So our signal space is basically a vector space. It's a vector space that covers communication signals. And this vector space will represent the M symbols in a constellation. And since we're talking about a discrete number of symbols, M, countable, discrete, that means that the vector space that we'll be working with is a finite vector space. If I have M symbols, the largest dimension that this space can be is M dimensional. And we'll see that sometimes it can be of a smaller dimension. Now, that's true for my signals because I have a finite number. But what about noise? In the case of noise, noise can be anywhere. It's not just in the structure of the M signals that I decide that I will transmit. So noise has a vector space as well, but this vector space, the noise space, is of infinite dimension. But we'll deal with these two issues, and we'll see that it's not the noise everywhere that matters. It's just the noise in my signal space that it will be important. But we'll develop that mathematics. But just to start out, the idea of using a space is using a vector space, and the vector space will be finite dimensional for the signal, infinite dimensional for the noise. So, you know, what is a vector space? A vector space has been, you've studied it, you know, before university, at university. So you've seen vector spaces in many forms. The most common vector space that we deal with is the three-dimensional vector space, such as the one that's shown here. And vector spaces are defined by different characteristics. It has to have an origin. The origin is included. There's a set of basis vectors. We have an inner product, an outer product. So there are various manipulations we can make on a vector space. For now, let's just say that, you know, we have this geometric intuition. What is a vector space? And now what I want to do is try to take that intuition we have for physical spaces and try and think of it in terms of a signal space. What's different when we talk about signals? Well, when we talk about signals, that means that I'm going to take a waveform, which is a function of time, and our basis vectors which are sort of shown here, are also vectors, are also functions of time. So when I talk about the x-axis represents a basis vector, and that basis vector is a function of time. The y-axis represents another basis vector, etc. And so now when I see here a vector in this vector space, this vector space represents also a function of time. It's the waveform, for instance, for the mth symbol in my constellation. So this is where we do this abstraction, which is a little different for vector spaces. And so the discussion today is to just make you comfortable with this, how do I represent a function of time as a vector with some coordinates? I mean, how does that work? And that's really the Schmidt process. So we start with this idea This is a vector space. This is a signal space, which is a vector space which represents signals. And now we're going to show you, like, physically, how do I take a set of signals and turn it into a representation in signal space. So I'm going to start with a very simple example, and I'm going to take 3 symbols. And these 3 symbols are the ones that you see here. They're square waves. In this case, it's like having a +1, -1, and then a 0. And this is the time of a symbol. And in the second symbol, I start out at 0, I go up to +1, down to -1, and then I'm over. And in the last symbol, the waveform is +2, down to -1, stay to -1. So the symbol time is 3 seconds, and I have 3 different symbols, each with a different waveform that I've chosen. And what I would like to show you is that this collection of symbols can be represented by these 3 vectors. This is the signal space, and these are the 3 vectors. So the concept is I have functions of time, and those functions of time I represent as vectors in a vector space. I'm going to show you now the process. The Schmidt process actually gives me the coordinates of these vectors. So the concept is I have functions of time. Functions of time become vectors in a vector space. And how do I get from functions of time into the coordinates for what this vector space is? How do I find the basis vectors? That's part of this Schmidt process that I will take you through. So now let's get back to, like, what is a vector space? A vector space is described by a collection of basis vectors. And of course, there doesn't have to be an orthonormal basis, but orthonormal bases are easier to work with. And an orthonormal basis means that the ortho means that all the basis vectors are orthogonal to one another. So that means that this 0, whenever I have the inner product, okay, so let's back up a little. This is the set of basis vectors. And remember, what is a basis vector? Basis vectors, the collection of basis vectors is a collection that spans the space. So all of these basis vectors together will allow me to reach into any corner of the space that I want. It spans the space. So any collection of vectors that spans the space, so that I could take a linear combination and reach any point in the space, they form basis vectors. Then I want orthonormal basis vectors, and for those I have particular properties, and that has to do with the inner product. So inner product is represented by this notation of the 2 angled brackets. And if I take the inner product of any 2 basis vectors, I and j, and these 2 vectors are distinct, they're not the same vector, and they give me 0. That means they're orthogonal from one another. So all these basis vectors are orthogonal to one another. And if it's orthonormal, the normal, of course, refers to the 1. That if a inner product of a basis vector with itself gives you length 1. So this is a convenient basis. The basis is not unique. There's an infinite number of bases for a vector space. And even the collection of orthonormal bases are not unique, but it might as well restrict ourselves to a set of bases which is convenient to use. So inner product is something that you learned in our geometric vector spaces. And now what does it mean when I talk about an inner product, when I'm talking about functions of time? So I have to really define an inner product for this basis, for this vector space, which is a signal space. So this is the definition given for the inner product, and it's basically a correlation of 2 signals across the time of one symbol. So I take the integral of the product of 2, so here are, in this case, 2 basis vectors. So the inner product of these 2 basis vectors is just the integral of the product of the basis vectors with integration over the time of one symbol. So this is an inner product definition good for any vectors in the space, and in this particular case, I'm applying it to the basis vectors. So if I have m symbols in the vector space, I'm going to call n the dimension of the space. N equals the dimension of signal space. So you'll notice that I said that there were a collection of basis vectors, and the number of basis vectors I had went up to capital N, and that means that the dimension is of capital N. So if I have m symbols, m becomes an upper bound on the dimension of the signal space. So the largest that my signal space is going to get is going to be m, because I have to represent m symbols in it. But it's possible that n, the dimension, could actually be smaller. And in fact, that's quite common and something that we will examine in the coming weeks about this choice and the impact of this choice. So this is a very important concept, so I'm trying to bring your attention to it early on. Okay, so I'm representing a signal, in this case one of my symbols, in a vector space. So I've described that there is some basis that I'm going to use. I'm going to find a set of basis vectors. And now what do I do with these basis vectors? I use these basis vectors to represent the signal. In fact, there's m signals, so I is one of m, so I is some element between 0 and m minus 1, I suppose. And when I say that I can represent this as a vector, that means that it becomes a linear combination of basis vectors. So that's why I have basis vectors, because I can use them as building blocks to form any vector in the space. So I want to reach the signal, Si, and the way I reach it is by doing this linear combination. And so here, these coordinates, these coefficients are the coordinates of the symbol in this signal space. So I make a linear combination. It's a weighted linear combination, and the weights, the coefficients, become the coefficients of the signal. So if Si of t is my signal in time, here is my representation of this signal as a vector. So it's a vector. What's a vector? A vector is a collection of coordinates. My dimension is size n. That means I need a collection of n coordinates to tell me what the vector is in this vector space. And so these coefficients are simply the coefficients in the linear combination for a given basis vector. And how do I find what are these coordinates? How do I determine what the coordinates are for a given? Well, that is exactly the these coefficients can be found quite simply by taking the inner product of the symbol with the basis vector. And remember, the inner product of the signal and the basis vector, well, that's just an integral. So if I know the time functions, which are my basis vector, and I know the symbol waveform, then I just calculate this inner product, I get a number, and that becomes that coefficient. And then I move on to the next basis vector. And the demonstration that this is indeed, if I use the inner product, if I take this, use the inner product, I'm going to get some of these AIs. And are these AIs, then if I put them into this equation, that I will actually get SI back? Well, that's a simple demonstration. So this simple demonstration says that suppose that SI can indeed be represented by this linear combination. Then I put the linear combination inside of the inner product. So I take this equation, put it here, and I take the inner product with, in this case, the kth vector. And I know that this is a linear operation so that I can take the sum out, and this is of course just a constant. So it becomes the sum over aij times the inner product of cj with ck, but of course these are orthogonal. So only j equal k is non-zero. So I have a sum, but the sum disappears because all of them are zero except for one element, the one element when j equals k. And that one gives you a 1. So this just shows that these two equations are complementary. You know, they give one another. So this is where I get that the way I find this coefficient is by this inner product. So the last important observation is that what is the 2 norm of this vector? Well, we know that if we want to know the length squared of the vector, then we would just sum up the square of the coefficients. And so this is the norm that we will be using in this signal space. So let's think about what is that that norm that we're just talking about. Let's expand on this idea now on the next slide. So I take this 2 norm, which is by definition the inner product of the vector with itself. And I go back to the definition of what is the inner product, and then what that means is I'm integrating the signal squared over the time of one symbol. And so essentially what I'm calculating is the signal energy. So in this vector space, it's really, really an important concept. The length of the vector is proportional to the signal energy. In particular, the length squared is equal to the signal energy. And that means that the longer a vector is that represents a signal, it means the more energy there is. So that's something that's really cool because I can look at a vector representation and know something right away about these signals. Let's go back. Here, I have a long one, a short one, and a medium one. So right away I know that these 3 signals have unequal energy. So this is a very nice part of the intuition that we gain from going to a vector space. So because we're going to be working with constellations where the energy per symbol is not necessarily constant, that there could be some symbols with more energy, some with less energy, some with no energy, I don't send anything. So in that case, it's an important parameter that will be associated with any constellation is the average energy per symbol in the constellation. And it's quite easy to give a definition. So I just average over all the signal energy, and that gives me the average energy per symbol. And this will give me a way to compare fairly different kinds of constellations. Okay, so far I've been talking about how do I represent a signal in signal space. But now I got to talk about noise, because remember, noise is where it's at. That's what the basis of this whole course is. How do we deal with noise? If we didn't have noise, it'd be easy to send information from one place to another. So what happens when I add noise? Well, the transmitter sends a vector. It sends, symbol Sj, for instance. However, when I get to the receiver, what I get is Sj plus some noise. So that means that instead of landing right at the precise point that was transmitted, when I examine the signal space at the receiver, what I get is displacement. So every time I send that same symbol, I get added to it a different noise. And if I take the sum of those 2 vectors, I get a new position. And so all of these represent different transmission of the same symbol but different noise. And so it creates like a cloud around the symbol point. So I know at the receiver, these are the points that the transmitter is sending. But what I'm seeing is not just these, in this example, 2 points, but instead there's like clouds around those 2 points. Again, what's great about this representation in signal space, this geometric interpretation, is that we get a lot of intuition. So imagine I have a little cloud or a big cloud. Well, a little cloud means the noise is less powerful. Larger cloud, the noise is more powerful. And of course, if the cloud is about the same size but the vectors are short, that means that the clouds get closer together. Signal to noise ratio is not good. So clearly, this idea of signal space is going to help us in understand what's going on, what's a good strategy if I chose different ways of representing signals, what would the impact in the space be, what would be the impact of having noise in the space. So this is why we look at signal space analysis. But this idea is of what would it look like when I add noise. It does look like a cloud. And the smaller the cloud is, the easier it is to distinguish what was transmitted. Like there don't seem to be any received signals anywhere in between here, right? So you think, oh, well, it's not too hard to figure out. When I see this here, I'm going to guess that it was an SJ sent and not an SK. And so now we're getting into decision algorithms. How do I decide what was transmitted? So this is where we're going with this signal space analysis. But now the question is, how do we deal with noise in the vector space? Because as I mentioned, noise does not necessarily fall in the signal space. Noise can be anywhere. It doesn't have the structure that it's only one of several signals. So the noise space is of infinite dimension. It can fall anywhere, which means that I have to have an infinite dimensional set of, I have to have an infinite number of basis vectors to span this infinite dimensional space. But what I'm going to do is I'm not going to throw away what I already did. I'm going to start with it's like a subspace. The signal space is a subspace of the noise space. So I'm going to start with that subspace, and I'm going to use those first and basis vectors to describe the larger noise space. I'm just going to extend it. I'm going to add more basis vectors in order to make sure that I span the whole noise space. So then, of course, when I represent the noise contribution at the receiver, it will have a vector representation, and of course it'll have an infinite number of coefficients. And just as I saw with signal space, each one of the coefficients inside of this noise vector can be found by taking the inner product of this noise function of time, this random process, taking the inner product with each one of the basis vectors in turn. And the first n basis vectors were formed by my signal space, and after that, of course, they're more arbitrary. So now I want to have one vector space that describes everything. I want to have one vector space that represents the noise and where the signal falls in it. Well, that's easy, because now I take this extended basis for the noise, and the symbol, well, if I want to know what are the coordinates in this larger space, well, the larger, the basis vectors after the nth basis vector, they'll always have zero contribution because I've already represented the signal in the n-dimensional space where it falls. So the symbol, the vector, excuse me, for that symbol in this larger dimensional space is just the coordinates I've already found, and I tag on a bunch of zeros. Quite straightforward. Okay, so now I have a vector space where I can represent the received signal. I had a signal space which was sufficient for representing what the transmitter did, and now at the receiver I've expanded it to cover all of where the noise is. So instead of writing it in this time domain representation, I can do a vector version of the time domain. So now we get to the gritty part. How do I actually find the coordinates? So I have a received vector, an R of t, and I want to know, how do I get the coordinates? Well, to get the coordinates, yeah, sure, I take the inner product. Ri is the inner product of Rt, Ci of t. Okay, I have a received signal in time. I can do an integral, that's okay. But I gotta know what the basis vectors are. So how do I find out what those are? And that is what the Gram-Schmidt process is about. And so I go back now to my previous example. How was it that I found those vectors from those square waveforms? How can I go from one to the other? And that is the Gram-Schmidt process. And the Gram-Schmidt process is just like a recipe. You just go through the steps and it'll kick out what you need. Very, very simple. So I will go over with you now what is the Gram-Schmidt process for generating a collection of orthonormal basis vectors from a collection of symbols. So I have here a collection of m symbols, m functions in time, and I want an orthonormal basis. So the first thing I do is I say, step one. This is a recipe. I'm just going step by step. Step one. Start with the first symbol. It doesn't matter which one. Start with one of them. And I say, well, that's going to be my first basis vector. I said it was going to be an orthonormal, so I have to normalize it. So I don't know what the energy of that symbol is. But first thing I do is I normalize by that energy. So I calculate what is the energy of the first symbol. Then I divide that by the square root of the energy, and that becomes my first basis vector, which now has unit energy. Step one basis vector. Now we go on to step two. In step two, I now take the next symbol, and I use the next symbol as my core that lets me get the next basis vector. So what have I got? I've got basis vector number one already, and then I take my second symbol, and this is what I use. So I already have one basis vector. And so I say, well, how much of this new symbol can I represent with the basis vector I've already created? So C1 is the first basis vector, and this inner product that we see here. The inner product, if you recall from your geometric interpretation of an inner product, it's a projection of one vector onto another. And so now we're looking at the projection of S2 on C1. Of course, C1 is just symbol 1 because that's how I chose it. But basically, I have a previous basis vector. I project the new symbol onto that, and that part of the symbol I can represent already with the basis vector. So I get that coordinate. That's the coordinate in that first basis vector, and I multiply by the basis vector, and that is the projection. So now I take my S2 and I subtract off that. So now I've taken away all the parts of S2 which can already be represented by C1. And what's left is what cannot be represented by C1, and that becomes C2, my second basis vector. So here we have, it's an intermediate step. We call it theta 2 because it hasn't been normalized yet. But basically I take S2 minus its projection onto the previous basis vector. That gives me theta 2, and I take theta 2 and I normalize its energy, and that gives me the second basis vector. So you can see now the idea of the process is to start with one, go on to the next one, strip off what I already know, what's left, something new, and becomes the new basis vector. So now when I go on to the next stage, it's basically repeating this technique. So I start with a new basis vector, Si, and I subtract from it all the projections on all of the previous basis vectors that I've created. So here's a sum over I, sum, because it's a whole bunch of previous projections. And at the end I get theta I, which is the new innovation, the new part that hasn't been represented by the previous basis vectors. And once again, do a normalization so that I end up with a normalized basis vector. So it could happen that you would get to a step where there's nothing left, right? You arrive at a symbol which can already be represented by all the previous vectors. Okay, so that one, you move on. It doesn't create a basis vector, you move on. And you keep doing that until you get through all of your symbols. So this is why sometimes the dimension could be smaller than m, because it could be that some of your symbols can be represented as a linear combination of previous symbols. So that is a common exam question. So, you know, why is it that the space could be n less than or equal to m? And that's when this happens, when some intermediate step, you find a symbol that has been the linear combination of previous ones. Of course, eventually, even if none of them are linear combinations of other ones, then it's going to go on to the bloody end when you finally get to n. And then the space will have dimension m, but of course the process will stop because you ran out of symbols. So that takes us to our example. And so now we're just going to go through a little bit of mathematics and apply the Schmidt process, which we've described. We're going to apply it to these three symbols. So we'll start with the red, symbol 1. And I first calculate the energy. So I do the integral over the symbol time. Symbol time is 3 seconds. So here I have from 0 to time 1, the signal is 1. So I have part of the integration, which is 0 to 1. Then the next part, the signal is -1. And so I have -1 squared, and now my integration is from 1 to 2. And of course, there's no integration from 2 to 3 because the signal is 0 there. So this gives us that the energy is equal to 2. And so I divide my original symbol by the square root of 2, and that gives me my first basis vector. So my first basis vector looks just like S1, but I've modified the amplitude so that the energy is a unit. Now we get on to step 2. In step 2, the first thing I have to do is calculate the inner product of S2 with the newly found basis vector. So here's the basis vector I found on the previous slide. Here is the definition of the function, the second symbol. So now I just have to calculate the inner product of these two. I have to calculate the integral of the product over the interval from 0 to 3. So I break it up. There's three different zones of definition of each of these functions. So I break up the integral from 0 to 3 into the 3 sections, 0 to 1, 1 to 2, 2 to 3. And in each one of these integral, I substitute in the value for each one of these functions during this interval. So S2 is 0 here, C1 is 1 over the square root of 2, etc. So now I just do the mathematics, and I arrive at the projection as being -1 over the square root of 2. So now I'm ready to calculate theta 2. And theta 2, I just take my original symbol S2 and I subtract from it the projection onto C1. So I take that coefficient and I multiply it by the actual vector, and I do the subtraction. So I take this function here minus 1 over the square root of 2 of this function. So S2 and 1 over the square root of 2 of C1, and I do the math, and I come up with this result, that between 0 and 2 it's 1/2, and between 2 and 3 it's -1. Almost done now with finding my second vector, basis vector. It looks like this, except this one is not length 1. I want it to be length 1. And in order to have it be length 1, I have to normalize by the energy, and so that's the step. So I have to multiply by the square root of 2 over 3. And so with the normalization, this becomes my second basis vector. Now we go on to step 3. Now I have to calculate two projections. I have a new base, and I have a new symbol, and I take that symbol, I project onto the first one, I project onto the second one, That's going to give me two numbers, and then I take those numbers, I multiply it by these functions in time, I calculate the difference, and I come up with this new function in time. So we'll go through, again, I don't want to go through all the details, but it is available on the slides if you want to go over it. But basically this calculation of the projection of the third symbol onto the first basic vector gives me 3 over the square root of 2. The projection of the third symbol onto the second basis vector gives me 3 over the square root of 6. And now I do the math to calculate S3 minus 3 over the square root of 2, C1, minus 3 over the square root of 6, C2. So that is what's going on here. And what's interesting is we get here at the end, I get 0. Okay, so it's easy to make a mistake in the math and to not get 0. But if we do it carefully, we come up and we realize that finally symbol 3 is a linear combination of symbol 1 and symbol 2. We get it from C1, and C2 of course is a combination of C1 and S1, so S2. So ultimately, this is because S3 is a linear combination of S1 and S2. Now maybe that wasn't obvious when we looked at them at the beginning, but you could go back and confirm this characteristic. But when we have a basis vector which comes to 0 before we've gotten to the last symbol, that means that there is some linear combination of this previous symbols for this symbol. So what that means is we don't have 3 basis vectors, we only have 2 basis vectors. That means that our space is of dimension 2. And if you recall, when I gave you my answer at the beginning, we saw that we only had a 2-dimensional space that we were writing these vectors in. So the last part is just figuring out what are the coefficients in this basis. We have the basis vectors. Now I want to represent the symbols in this basis, and to represent them I have to calculate their coefficient. But actually we've done this during the Schmidt process. So we're not actually going to do any new calculations, or not many. We're just going to look back at what we've already calculated. So for instance, S1 inner product with C1 gave us square root of 2. And of course, by construction, S1 is orthogonal to all of the other basis vectors. Always will be. S1 will always, if you use a Schmidt process, S1 will have a number and then all zeros. S2 will have a number, and then all zeros. By construction, that's what this approach is doing. The inner product of S2 with C1 we found in our step previously. We know what that coefficient is. We do have to calculate the coefficient with the inner product of S2 and C2, and when we do the math we come up with 3 over the square root of 6. And of course for the third symbol we have already calculated the coefficients with C1 and C2. So these calculations of coefficients allow me to write the coordinates, the coefficients if you will, of each one of these signals. So now we know where I got this plot, which I showed you previously. So S1, of course, by construction lies along the first basis vector, and its length is the square root of 2. And if we look at S2, we have its basis vectors as minus 1 over the square root of 2, and then 3 over the square root of 6. And the length of this is also square root of 2. Previously I said they were different lengths, but my eyes weren't good. They're actually the same length. But we can see that S3 is now square root of 6 is the length of S3. So we can get from these coordinates, we can plot these vectors, and we have a representation of these particular signals in a signal space. Thank you.